Welcome to the HVAC Source Equipment for Cooling Part 2 module. In this course, we will explore the various technologies and systems that power cooling solutions in HVAC systems. From innovative air cycle systems and absorption refrigeration to advanced evaporative cooling techniques, this module will provide you with a comprehensive understanding of their principles, applications, advantages, and limitations. Let's discover the air cycle system, a unique refrigeration method that uses air as the refrigerant, avoiding traditional chemical refrigerants. It operates differently from conventional systems, as it doesn't involve the vapor-liquid phase change commonly seen in other refrigeration cycles. Here's how it works. Compression of air. The process begins with the compression of air, which increases its pressure and temperature. This step is essential for preparing the air for cooling in the next stage. Heat exchanger cooling. The high-pressure, high-temperature air then passes through a heat exchanger, where it is cooled. This process removes excess heat from the compressed air, preparing it for expansion. Expansion and cooling. After cooling, the air passes through an expansion device. This reduces its pressure and temperature, resulting in chilled air. Application in aircraft. The air cycle system is most commonly found in aircraft air conditioning systems, where its lightweight design, environmental safety, and efficiency at high altitudes make it an ideal choice. The image you provided appears to be a schematic diagram of an air cycle machine used in aircraft environmental control systems. Air cycle machines are used to provide conditioned air to the cabin of an aircraft. Here's a breakdown of the key components and their functions. Ram air inlet, draws in ambient air from outside the aircraft. Low limit valve, regulates ram airflow to prevent excessive cooling. Reheater, adds heat to conditioned air for temperature control. Condenser, removes heat and moisture from the air. Water spray nozzle, injects water for cooling and humidity control. Air cycle machine, core compresses, cools, and reheats air for conditioning. Economy cooling valve, regulates airflow through the economy cooler. Water collector, collects condensed water. Conditioned air check valve, prevents backflow of conditioned air. Conditioned air distribution system, delivers conditioned air to the cabin. Bypass check valve, allows air to bypass the air cycle machine in certain conditions. Ram air exhaust valve, releases excess air from the system. Second stage turbine bypass valve, regulates airflow through the second stage turbine. Let's cover the absorption refrigeration. Absorption refrigeration is a specialized cooling system ideal for large-scale applications where steam or waste heat is available. It shares similarities with the vapor compression cycle, using components like the condenser, expansion device, and evaporator, but replaces the mechanical compressor with a chemical process. The cycle begins with low pressure, low temperature refrigerant vapor being absorbed into a liquid solution in the absorber. A pump then raises the pressure of this solution, requiring minimal energy compared to compressing vapor. In the generator, heat is added to release the refrigerant vapor from the solution. This vapor enters the condenser, where it cools and transfers heat to the atmosphere, condensing into a liquid. After passing through the expansion device, the refrigerant becomes low pressure, low temperature liquid and enters the evaporator, absorbing heat to create a cooling effect. Finally, the refrigerant vapor returns to the absorber, completing the cycle efficiently and sustainably. Here's a breakdown of the working process of a vapor absorption refrigeration cycle. Generator, a strong ammonia water solution is heated in the generator, causing the ammonia to evaporate, leaving behind a weak solution. The evaporated ammonia is a high-pressure vapor. Condenser, the high-pressure ammonia vapor is cooled and condensed into a high-pressure liquid. Expansion valve, the high-pressure liquid ammonia passes through this valve, reducing its pressure and temperature. This low-pressure, low-temperature ammonia enters the evaporator. Evaporator, the low-pressure ammonia absorbs heat from its surroundings, causing it to evaporate. This cooling effect is used to cool the desired space. Absorber: the low-pressure ammonia vapor is absorbed by the weak ammonia water solution from the generator, forming a strong ammonia water solution again. Pump: the strong ammonia water solution is pumped back to the generator, completing the cycle efficiently. The vapor chiller refrigeration cycle works by circulating a refrigerant in a closed loop. The refrigerant absorbs heat from the evaporator, vaporizing as it does so. The vapor is compressed, raising its pressure and temperature. It then releases this heat to the condenser, condensing back into a liquid. The liquid refrigerant expands through an expansion valve, dropping in pressure and temperature. This low pressure, low temperature liquid returns to the evaporator, repeating the cycle and providing cooling. Let's learn about the advantages of absorption refrigeration. Lower energy costs. Absorption refrigeration systems are cost-effective because they often rely on low-cost gas utility rates, especially in summer. Eco-friendly. These systems do not use chlorofluorocarbons, making them environmentally safe and sustainable. Quiet operation. Unlike vapor compression systems, absorption systems operate with minimal noise and vibration, providing a quieter environment. Reduced electrical demand. They require fewer electric auxiliary components, contributing to lower operational complexity. Efficient heat utilization. These systems can effectively utilize waste heat or renewable energy sources, enhancing their efficiency and sustainability. Disadvantages of absorption refrigeration. Higher initial cost. Absorption refrigeration systems have a higher upfront cost, typically about 15 to 20% more than vapor compression systems. Lower energy efficiency. With a lower coefficient of performance, absorption systems are generally less energy efficient than vapor compression systems. Waste heat dependency. These systems are most practical when waste heat is available, as this source of energy is essentially free, offsetting operational inefficiencies. Increased heat rejection. Absorption systems reject more heat, necessitating larger and more expensive auxiliary components like cooling towers and condenser pumps. Let's examine the thermoelectric systems. Principle of Peltier effect. Thermoelectric systems operate based on the Peltier effect, where an electric current passing through two dissimilar materials generates heat at one junction and creates a cold surface at the other. Semiconductor application. The Peltier effect is applied in semiconductor refrigeration to produce cooling efficiently. Advancement in technology. The development of semiconductor materials during the 1960s enabled the commercial adoption of thermoelectric systems for refrigeration. This technology is compact, silent, and suitable for small-scale cooling applications. The tech in the image utilizes the Peltier effect, a phenomenon where an electric current passed through a junction of two dissimilar conductors causes a temperature difference across the junction. In this device, a DC power supply provides the current to the junction formed by the N-type and P-type semiconductors. The N-type semiconductor absorbs heat from the water source, while the P-type semiconductor rejects heat to the surrounding environment. The heat absorbed by the N-type semiconductor is carried by electrons, which migrate towards the P-type semiconductor due to the applied voltage. These electrons collide with atoms in the P-type semiconductor, releasing their energy as heat. The heat is then dissipated to the environment through the heat sink and cooling fan. The ceramic substrates and copper plate enhance the heat transfer process. The insulation prevents heat loss to the surroundings and ensures efficient operation of the tech. Let's understand evaporative cooling, a process where coolers, also known as swamp coolers or desert coolers, use evaporation to lower air temperature. As water evaporates, it absorbs heat from the surrounding air, resulting in cooler air. Historical trend. The popularity of evaporative coolers has declined since the 1950s due to the prioritization of lower initial costs over long-term operational savings. Cost effectiveness. These systems can be highly cost-effective and energy-efficient under suitable conditions. Optimal use. Evaporative cooling is particularly beneficial in regions with low outdoor wet bulb temperatures, and during specific hours when these conditions prevail. How evaporative cooling works. Evaporative cooling systems operate on the principle of evaporative cooling, a natural process where water absorbs heat from its surroundings as it evaporates, resulting in a cooling effect. In this system, hot, dry air is drawn into the unit. The air passes through a wet evaporative pad, where water is distributed. As the hot, dry air comes into contact with the wet pad, some of the water evaporates, absorbing heat from the air and lowering its temperature. The cooled air is then blown out of the unit, providing a refreshing breeze. The water reservoir at the bottom of the unit ensures a continuous supply of water to the evaporative pad, maintaining the cooling process. This type of cooling is particularly effective in dry climates where the relative humidity is low, allowing for efficient evaporation and significant temperature reduction. Let's quickly break down how it works and why it's efficient. Direct evaporative cooling pulls 100% outdoor air into the system. The air is cooled by coming into direct contact with water as it evaporates. This cooled air is then sent indoors, creating a comfortable environment. To maintain balance, the system uses simultaneous air exhaust to regulate airflow. When designing a direct evaporative cooling system, you'll want to consider space needs, air filtration, and delivery mechanisms to ensure it operates effectively. One of the main advantages is its cost efficiency. Evaporative cooling uses significantly less energy than traditional refrigeration systems, making it a great choice for hot and dry climates. There are two main system types. Spray-type air washers. These spray fine water droplets into the air, cooling it as they evaporate. Wetted media type coolers. These use water-saturated media that air passes through, cooling it during evaporation. Both are great options depending on your space and application. Direct evaporative cooling is a simple, sustainable, and cost-effective way to cool air naturally. The image you provided illustrates an indirect direct evaporative cooling system. This system works by utilizing two air streams and a cooling medium, typically water. Warm air is drawn into the system and passes through an indirect evaporative cooling section. Here, the air is cooled as it exchanges heat with a secondary air stream that has been humidified by passing through a wetted media. The secondary air stream, now saturated with moisture, is then exhausted from the system. The primary air stream, now cooler and drier, then enters the direct evaporative cooling section. In this section, the air is further cooled as it passes through a wetted media, where water evaporates and absorbs heat from the air. The resulting cooler and slightly more humid air is then delivered to the desired space. This system is efficient in cooling and humidifying the air, making it suitable for climates with low humidity. The image you provided illustrates a wetted media evaporative cooler. Here's how it works. Warm air enters the cooler and passes through a wetted media pad. Water is pumped into the pad, saturating it and providing a large surface area for evaporation. As the warm air passes through the wet pad, the water absorbs heat from the air, causing it to evaporate. This evaporation process cools the air significantly. The cooled air then exits the cooler and is distributed to the desired area. The water that evaporates is replenished by a float valve system, which maintains a constant water level in the sump. Excess water is drained away through a sump drain. This type of cooling system is particularly effective in hot and dry climates where the low humidity allows for efficient evaporation and cooling. Let's explore how it works and where it can be used effectively. Indirect evaporative cooling is a versatile system, suitable for a wide range of climates and different occupancy types. This makes it much more adaptable compared to direct evaporative systems. Here's how it works. Secondary air is cooled through evaporation on one side of a heat exchanger. The cooling is then transferred indirectly to the primary supply air through the heat exchanger walls. This ensures that the supply air stays free from added moisture, unlike direct evaporative systems. Now, let's talk about temperature constraints. The system's cooling performance depends on the wet bulb temperature of the secondary air. The supply air's leaving dry bulb temperature cannot drop below this level. Indirect evaporative cooling has a few key applications. Pre-coolers, they're used to precondition air before it enters further processing. Condenser coil efficiency, they enhance the performance of condenser coils by lowering the air temperature around them. Indirect evaporative cooling offers efficient, effective, and flexible solutions for air cooling while keeping air moisture levels under control. The image you provided illustrates an indirect direct evaporative cooling system. Here's how it works. Warm air enters the cooler and is drawn through a heat exchanger, indirect section, where it comes into contact with a cool secondary airstream. This secondary airstream is cooled by passing through a wetted media pad, where water evaporates and absorbs heat from the air. This heat transfer cools the secondary airstream without adding moisture to the primary airstream. The cooled secondary airstream then transfers heat to the warm primary airstream through the heat exchanger, further cooling it. The cooled primary airstream then passes through a second wetted media pad, direct section, where it is cooled further by direct contact with evaporating water. This final stage adds some humidity to the air, but the overall cooling effect is significant. The cooled air is then exhausted, providing a comfortable environment. Let's dive into how they work and their role in humidity control. Desiccant systems are widely used to manage and maintain humidity levels in air conditioning and cooling systems. They ensure the air stays dry and comfortable, improving air quality and system efficiency. Here's how it works. Moisture absorption is the key. Desiccant systems use materials designed to absorb water like a rotating drum filled with solid desiccant. As air passes through these materials, moisture is pulled out, leaving the air dry. Once the desiccant becomes saturated with moisture, it needs to be regenerated. This is achieved by heating the air that passes through the desiccant, which releases the trapped moisture back into the environment. A unique feature of desiccant systems is their continuous operation. The rotating drum allows part of it to dry incoming air while another portion is exposed to hot air to release the moisture. This ensures smooth, steady, and efficient operation at all times. Desiccant systems are effective, reliable, and essential for consistent humidity control. Let's explore how this innovative system works and its key benefits. The liquid desiccant cooling system operates in a cyclical process to cool and dehumidify air efficiently. Here's how it works. First, ambient air is drawn into the system and passes through a liquid desiccant, usually a hygroscopic salt solution like calcium chloride or lithium chloride. These desiccants are highly effective at absorbing moisture from the air, which leads to both cooling and dehumidification. After the air is conditioned, it is supplied to the space that needs cooling. At the same time, a portion of the exhaust air from this conditioned space is captured and used to regenerate the desiccant. This moist exhaust air heats the desiccant, releasing the absorbed moisture back into the air. The system stores the concentrated desiccant for future use, while the diluted desiccant returns to the dehumidification process to maintain a continuous cycle. Let's break down the key systems and how they're used in refrigeration processes. First up, induction motors. These motors are widely used to drive refrigeration compressors because they are efficient, reliable, and perfect for managing the mechanical power needed in refrigeration applications. Induction motors ensure smooth and consistent operation in refrigeration systems. Next, we have turbine-driven systems. These systems utilize gas turbines or steam turbines to power centrifugal compressors, especially in applications where natural gas is readily available and cost-effective. Turbine-driven systems are often the go-to choice for larger-scale refrigeration needs due to their high performance and efficiency. Now, let's talk about the piggyback system. This is an innovative setup commonly found in large buildings. It combines both gas and steam turbines to optimize energy use for refrigeration. Here's how it works. A boiler generates steam, which drives a back pressure turbine. This turbine powers a centrifugal chiller, effectively combining gas and steam energy to achieve efficient and powerful refrigeration. Let's continue exploring more about prime movers and how they integrate waste heat recovery and energy optimization into modern refrigeration systems. First, let's talk about exhaust heating. The exhaust from a steam turbine can actually be put to good use by heating an absorption chiller. This not only improves system efficiency but also utilizes what would otherwise be waste heat to support the refrigeration process. Next, we have gas turbine exhaust. These exhaust gases can be directed to a heat recovery boiler, which then generates steam for the absorption unit. Now, consider the combination of steam turbines and absorption units. In certain systems, the steam turbine-driven compressor has approximately half the capacity of the absorption unit. Let's move on to cogeneration systems. Also known as combined heat and power, these systems are becoming increasingly popular because they do two things simultaneously: generate electricity and utilize waste heat for powering prime movers like turbines or compressors. Finally, let's touch on variable speed drives. Variable speed drives are a fantastic way to reduce energy consumption. They adjust the speed of fans and motors based on real-time demand, ensuring that energy isn't wasted when full capacity isn't necessary. The illustrated system represents a cogeneration system, also known as a combined heat and power system. This technology efficiently utilizes the waste heat generated by an internal combustion engine to produce both electricity and useful thermal energy. Working process. Electricity generation. The internal combustion engine, fueled by a suitable energy source, example, natural gas, diesel, converts chemical energy into mechanical energy, which is then transformed into electrical energy through a generator. Heat recovery. The engine's waste heat is recovered through several methods. Oil cooler, cools the engine oil, capturing heat energy. Jacketing, recovers heat from the engine's outer surface. Exhaust heat recovery, extracts heat from the exhaust gases. Thermal energy production. Hot water generation, the recovered heat is used to generate hot water in an auxiliary boiler. This hot water can be utilized for various purposes such as domestic hot water, space heating, industrial processes. Chilled water production. An absorption chiller, powered by the recovered heat, produces chilled water for cooling applications like air conditioning. Let's dive into plate heat exchangers, a key component used in many HVAC and refrigeration systems for efficient heat transfer. First, let's understand the structure. A plate-type heat exchanger consists of a series of thin metal plates stacked between two end frames. These plates act as the primary medium for transferring heat between two fluids. Now, let's look at how heat transfer works. The design creates separate channels on opposite sides of the plates for cold and warm media to flow. This allows the two fluids to exchange heat efficiently without mixing. One major advantage of plate heat exchangers is their high efficiency. The large surface area of the metal plates ensures that heat is transferred quickly and effectively, making them highly effective in a wide range of applications. Finally, let's touch on the plate design. The plates are often gasketed and embossed, which enhances the heat exchange process by improving fluid flow. Now let's explore the uses of plate heat exchangers and how they contribute to efficient heating and cooling systems. First up, cooling chilled water. During winter, plate heat exchangers can effectively cool chilled water by using cooling tower water, helping to regulate indoor temperatures and maintain optimal conditions. Next, they can act as a substitute for condensers or evaporators in different heating and cooling processes. This substitution allows for improved heat transfer efficiency while optimizing system performance. Plate heat exchangers are also widely used in solar thermal systems. They transfer heat between solar collectors and the fluid being heated, making renewable energy systems more efficient and reliable. Another important application is in thermal storage systems. These exchangers facilitate the heat exchange between thermal storage units and circulating water streams, improving both heating and cooling system energy efficiency. Lastly, plate heat exchangers can be used for heat recovery from hot refrigerant gases. Let's take a closer look at how a plate heat exchanger works and understand its key components. Now let's break down the key components that make it all work. Support columns and feet provide structural stability to the entire heat exchanger. An inspection cover allows for easy access to clean and maintain the system. A roller assembly enables the heat exchanger to open and close for maintenance and cleaning. The movable cover secures the plate pack and its gasket. The plate pack is the heart of the exchanger, containing the corrugated plates for heat exchange. A gasket seals the spaces between the plates to prevent any mixing of the fluids. The carrying bar supports the entire plate pack. Stud bolts secure the movable cover firmly to the frame. A guide bar ensures proper alignment of the plates for efficient operation. Tightening nuts and bolts hold everything in place. A lock washer ensures that these bolts do not loosen over time. The bearing box houses the roller assembly, contributing to smooth operation. A shroud encloses the plate pack to ensure safe and efficient operation. Lastly, the frame foot provides the necessary stability for the system. These components work together seamlessly, allowing the plate heat exchanger to transfer heat between two fluids efficiently using counter-current flow and a well-designed plate structure. Let's talk about condensers and evaporators, which are super important in air conditioning systems. They handle the heat transfer that makes cooling or heating possible. First, the condenser, it releases heat from the refrigerant into the air or water outside. Think of it as getting rid of the excess heat. Then, we have the evaporator. This one does the opposite. It absorbs heat from the indoor air, allowing the refrigerant to cool the space. Now, there are two types of systems. Air-cooled systems, these use air to transfer heat. They're simple, cost-effective, and work well in smaller spaces or places without access to water. Water-cooled systems, these are more efficient because they use water instead of air. You'll usually find them in larger buildings or commercial setups. So, whether you're using air or water depends on the system size, location, and how efficient you need it to be. Let's dive into air-cooled equipment, a common choice for many cooling systems. First up, size. Air-cooled systems are typically smaller and more compact compared to water-cooled ones. That makes them great for smaller spaces or applications where size is a concern. Next, effectiveness. While air-cooled equipment is convenient and works well for many situations, water-cooled systems are more efficient when it comes to refrigeration because they transfer heat better. Let's talk about water-cooled equipment and how it's used in larger systems. These systems are typically found in large commercial or industrial applications where high efficiency is a must. So, how does heat transfer happen in water-cooled systems? Well, it works through pipes, where water absorbs heat from the refrigerant and carries it away. This method allows for very efficient heat exchange. One common type is the shell and tube condenser. It has small pipes inside a shell that increase the surface area, allowing better heat transfer. But keep in mind, water-cooled systems have some challenges. They need larger diameter pipes for water circulation, and those can be expensive and take up a lot of space. This makes installation and maintenance more complex compared to air-cooled systems. Heat wheel. Energy recovery. A heat wheel, also known as an energy recovery ventilator, is used for exhaust air energy recovery. It helps in transferring heat from the outgoing air to the incoming air, reducing the need for additional heating or cooling. Airflow arrangement. In this system, the exhaust and incoming airflows are arranged side by side, allowing heat transfer between them. Heat absorption. The wheel contains a material that absorbs heat from the exiting airflow. As the wheel rotates, the heat is transferred to the incoming airflow, effectively preconditioning the incoming air. Working principle of heat wheel. Airflow interaction: warm air flows through one half of the wheel, while cold air flows through the other half. This allows heat transfer between the two air streams. Heat absorption: the fill material inside the wheel absorbs heat from the exhaust air as it passes through. Heat transfer: as the wheel rotates, the section of the wheel that has absorbed heat from the exhaust air is transferred to the incoming cold air, warming it. Continuous rotation: the wheel continuously rotates between the two airflows, maintaining the heat transfer process without interruption. Plate and frame heat exchanger: in contrast to the heat wheel, a plate and frame heat exchanger uses a fixed heat exchange area where the two airflows are kept separate. Moving heat exchange area: unlike plate and frame exchangers, the heat wheel has a moving heat exchange area, which makes it more dynamic and efficient in transferring heat. Contaminant transfer risk: there is a risk of contaminant transfer between the two airflows, particularly if there is air leakage or if molecules become attached to the rotating wheel. This needs to be carefully managed to maintain air quality. The image you provided illustrates a heat/enthalpy wheel system, a type of energy recovery ventilator. It works by transferring heat and moisture between incoming and outgoing air streams to improve energy efficiency. Outdoor air is drawn in and passed through one side of the wheel, while return air is drawn from the building and passed through the other side. As the air streams pass through the wheel, the moisture and heat are absorbed by the wheel's desiccant material. When the incoming air reaches the other side of the wheel, the desiccant material releases the stored heat and moisture, warming and humidifying the incoming air. This process reduces the energy needed for heating and cooling the building, resulting in significant energy savings. The drive motor rotates the wheel to ensure continuous transfer of heat and moisture between the air streams. Heat pipes. Waste heat recovery: heat pipes are commonly used for recovering waste heat in various systems, improving energy efficiency. Evaporation and latent heat absorption: when thermal energy is applied to one end of the heat pipe, the fluid inside evaporates, absorbing latent heat from the surroundings. Condensation and latent heat release: at the other end of the heat pipe, the vapor cools and condenses, releasing the absorbed latent heat into the environment. High thermal energy transfer: heat pipes can transfer more thermal energy than materials like copper, making them efficient at moving heat over distances. No moving parts: heat pipes operate without moving parts, which makes them reliable and low maintenance compared to other heat transfer devices. Heat pipe elements. Sealed container: the heat pipe is a sealed, hollow container that holds the working fluid and allows for the transfer of heat. Capillary wick structure: inside the heat pipe, a capillary wick structure helps to circulate the working fluid by capillary action. This structure draws the liquid back to the evaporator end after it condenses at the condenser end. Working fluid: the heat pipe contains a working fluid, typically a liquid, that evaporates at the hot end and condenses at the cooler end, transferring heat through the phase change process. Let's now discuss heat pipes and how they work. Heat pipes are fascinating devices that enable efficient heat transfer, and they're commonly used in electronics, HVAC systems, and other applications. A heat pipe has several key components. The container, which is the outer casing. The wick structure, which is a porous material lining the inside to transport the working fluid. The working fluid, the key player that changes phases between liquid and vapor. The evaporator section, where heat causes the working fluid to vaporize. The adiabatic section, which allows the vapor to travel without losing heat. The condenser section, where the vapor releases heat and condenses back into liquid. And finally, the end caps, which seal the heat pipe at both ends. So, how does it work? When heat is applied to the evaporator, the working fluid vaporizes. This vapor travels to the condenser section, releases heat, and condenses back into a liquid. Then, capillary forces in the wick structure return the liquid back to the evaporator, completing the cycle. This continuous cycle makes heat pipes highly efficient and reliable in transferring heat across different systems. Earth tubes. Stable underground temperatures. Earth tubes utilize the consistent, stable temperatures found underground to either heat or cool air, depending on the season. Pre-warming and pre-cooling. In the winter, cold outdoor air is pre-warmed by passing through the earth tubes, while in the summer, hot air is pre-cooled, reducing the load on HVAC systems. Temperature range. The underground temperatures typically range from 7 degrees Celsius to 24 degrees Celsius, providing a reliable source of energy-efficient heating or cooling. Effective in moderate climates. Earth tubes are particularly effective in regions with moderate climates where the underground temperatures remain within the ideal range for preconditioning air. Limitations in hot climates. In very warm climates, earth tubes may not be as effective because the underground temperatures may approach or exceed the desired indoor comfort levels, reducing their cooling effectiveness. The image depicts a cannet system, a traditional Persian irrigation system adapted for cooling in hot climates. The process begins with wind entering the wind tower, drawing hot air upwards through an access shaft. This creates a low-pressure zone in the cooled basement, causing cooler air from the underground cannet to rise and replace the hot air. The cannet, a network of gently sloping tunnels, draws cool air from deep underground where the temperature remains relatively constant. This cool air enters the basement, providing natural cooling. The system works on the principles of convection and pressure differences, offering a sustainable and energy-efficient solution for cooling buildings in hot climates. Geothermal heat pumps. Ground-coupled heat exchanger. A geothermal heat pump uses the stable temperature of the earth as a heat source in winter and a heat sink in summer, transferring heat through a ground-coupled heat exchanger. Higher heating efficiency. Geothermal heat pumps are significantly more efficient for heating, offering 50 to 70% higher heating efficiencies compared to conventional heating systems. Higher cooling efficiency. They also provide superior cooling performance, with 20 to 40% higher efficiencies than traditional air conditioning systems, making them energy efficient year-round. Ground source heat pump. Certainly, let's break down how a ground source heat pump works based on the provided image. Working process of a ground source heat pump. A ground source heat pump is a heating and cooling system that utilizes the constant temperature of the earth to provide energy efficient heating and cooling for a building. Heating mode. Ground loop. A network of pipes is buried underground or immersed in a water source. This ground loop acts as a heat source, extracting heat from the earth even in winter. Heat pump. The ground loop transfers heat to a working fluid in the heat pump's evaporator. Compressor. The heat pump's compressor compresses the refrigerant, raising its temperature and pressure. Condenser. The high-temperature refrigerant releases heat to the building's distribution system. Expansion valve. The refrigerant then passes through an expansion valve, where it expands and cools. Evaporator. The cooled refrigerant absorbs heat from the ground loop, repeating the cycle. Cooling towers. Let's start with the purpose. Cooling towers are used in HVAC systems to remove excess heat from the building, helping maintain a comfortable indoor environment. Function. They work by circulating water through a heat exchanger, where heat is transferred from the water to the air. Water circulation. The cooled water is then returned to the HVAC system to repeat the cooling process. Evaporation and maintenance. Cooling towers rely on evaporation to dissipate heat, which can lead to water loss. Regular maintenance is necessary to ensure their efficiency and prevent issues like scale buildup or contamination. This image shows a cooling tower. It's a heat rejection device that uses water to absorb heat from industrial processes or air conditioning systems. The cooling tower dissipates heat by evaporating a small portion of the water, which cools the remaining water for reuse. The fan at the top helps circulate air, while the water flows through the tower, being cooled as it moves down through the structure. Cooling towers are commonly used in large facilities such as power plants, factories, and HVAC systems for buildings. Thank you for completing the HVAC source equipment for cooling, Part 2 module. We hope this course has equipped you with valuable knowledge about innovative cooling technologies, their principles, applications, and practical insights. Our next session is chiller training outline activities.